So we talked about making pizza and how we can make what looks like a chemical equation out of a pizza recipe, right? So 1 crust, 5 ounces of tomato sauce, 2 cups of cheese, we can make 1 pizza. So let's say we have on hand 4 crusts, 10 cups of cheese, and 15 ounces of sauce. How many pizzas can we make? I hear 4. I hear 2. How do we figure this out? We'll have to stop making pizzas when we run out of an ingredient, right? So one thing we could do is we could start with the first ingredient and see, well, how many pizzas could we make using all of those? Well, that one's kind of easy. It's 4, right? But we could write that out. 4 crusts. And we can make 1 pizza for every 1 crust. So we could make 4 pizzas. Okay. What about 10 cups of cheese? Well, we can make 1 pizza. 1 pizza takes how many cups of cheese? 2 cups. Right? How do you know that? It says that in the recipe, in the equation. 2 cups of cheese are needed for 1 pizza. So if we have 10 cups of cheese, how many pizzas can we make? 5. But could we really make 5 pizzas? No, because when we made the 4th pizza, we'd run out of crusts, right? So then the cheese would just sit there. We can't make it into a pizza. And then the sauce, 15 ounces of sauce. And we get 1 pizza out of how many ounces? 5. So it takes 5 ounces of tomato sauce. So these units are going to cancel out, and that's going to give us 3 pizzas. So how many pizzas can we make? 3. We can only make 3. We have enough crusts for 4, we have enough cheese for 5, but we can only make 3 because we run out of sauce. Does that make sense? This is often what happens when you're cooking, right? You don't have exactly the right amount of flour and sugar and vanilla and eggs and everything for the cookies or whatever. There's one thing that you may run out of, and you've got plenty of the rest. So here's this in picture form. 4 crusts make 4 pizzas. 10 cups of cheese, we could make 5 pizzas. 15 ounces of sauce, we could make 3 pizzas. So the way we solve a problem like this is we look at each of the ingredients we have and we figure out how much product we could make. The actual amount that could be made is the smallest amount, because once you reach that smallest amount, you've run out of one of the ingredients or one of the reactants. The reactant, or the ingredient that gives you the smallest amount, is called the limiting reactant because it limits production. Everybody okay with that? So we call the tomato sauce here the limiting reactant, sometimes the limiting reagent. It's what makes the least amount of product. The maximum number of pizzas we can make, which is the smallest number that we came up with, is called the theoretical yield. Because if everything goes perfectly, in theory, you could make 3 pizzas. But as anyone who's ever cooked knows, sometimes things don't go as planned. So in a chemical reaction, it's the amount of product that can be made based on how much of the limiting reactant you have. The ingredient that makes the least amount of pizza, the least amount of product, is your limiting reactant, and that determines how many pizzas you can make or how much product, the theoretical yield. In a chemical reaction, it is most common that one of the reactants gets used up and there's extra of the rest. When that reactant is used up, the reaction stops. Just like when you're making pizzas and you run out of an ingredient, you have to stop making pizza. right? So the limiting reactant gets completely used up, gets completely consumed, and reactants that are not completely consumed are called excess. They're left over. So the actual amount that gets made is called the actual yield. This is not always the same. In fact, it's usually not the same as the theoretical yield. So if we think about the pizzas, what if, we put one in the oven and we get distracted watching videos of cute kittens on YouTube, right? And we don't hear the timer and it burns. Okay, we can't serve that pizza. So now instead of the 3 pizzas that in theory we should have been able to make, we only have 2. So our actual yield is 2 pizzas. There's lots of other things that could happen, right? I had a ceiling fixture fall and shatter while I was decorating a birthday cake once. I mean, crazy, just fell off the ceiling. Things happen, right? So how do we express the ratio of actual yield to theoretical yield? Give us a number to say, well, how well did we do? We use a percentage. So the percent yield tells us how efficient the reaction is, how efficient we are making pizzas. And the percent yield is the actual yield, how much you actually get, divided by the theoretical yield, times 100%. So if everything goes perfectly, and your theoretical yield and your actual yield are the same, your percent yield will be 100%. With the pizzas, if you made 2 when you could have made 3, the actual yield is 2, the theoretical yield is 3, you've got about 67%, which is not great. If you were working in a pizza place, they'd probably fire you for that. Any questions? So this is sort of a summary slide of these terms, and it's important to understand what these terms mean. Limiting reactant, the reactant that gets completely used up, the one that gives us the smallest amount of product. The reactant in excess is any reactant, there could be several of these, that there's more than enough of and there's some left over. It's in excess. Theoretical yield, if everything goes perfectly, that's how much could be made based on the limiting reactant. The theoretical yield is always calculated using stoichiometry. The actual yield is how much you actually make. In a word problem on a test or a homework assignment, we have to tell you what the actual yield is, because you would find the actual yield in an experiment by doing the experiment and weighing the product. So when we do an experiment in class, in lab, then you will actually be measuring the actual yield. But in a problem, it has to be given. And this is the equation for percent yield. So let's apply this to a chemical reaction. Go back to this methane combustion reaction. 1 molecule of methane, 2 molecules of oxygen. We can make 1 molecule of CO2 and 2 molecules of water. So this implies that every 1 molecule of methane reacts with 2 molecules of oxygen. If we have 5 molecules of methane and 8 molecules of oxygen, which one is the limiting reactant? We're going to do the same process we did with the pizza ingredients. So we're going to take the one reactant, the CH4, and we're going to figure out how much product could we make. So here we're interested in CO2. So 5 molecules of that, and we get 1 CO2 for every 1 methane. We could make 5 molecules of CO2. Then we'll take the other ingredient, the oxygen, 8 molecules of oxygen. Looking at the ratio from the balanced chemical equation, we get 1 CO2 requires 2 molecules of oxygen. So from these 8, we could make 4 CO2 molecules. 4 CO2 molecules is less than 5 CO2 molecules. Like 4 pizzas is less than 5 pizzas. We can only make 4 of these because we ran out of oxygen. Just like we ran out of the sauce in making the pizzas. So the oxygen is the limiting reactant. This amount of product is the theoretical yield. Everything goes perfectly, that's the most we could make. Any questions? So that's thinking in terms of molecules. Of course, we're dealing with masses more frequently. So when we've got masses, we have to go to moles and look at that. Now, this is the strategy that your book uses, and there's nothing wrong with it. It's entirely valid. If you want to do your problems this way, you go right ahead. So they say take the mass of the first ingredient, the first reactant, find out how many moles of product. Take the mass of the second, find out how many moles of product. Decide which of these is smaller, and then finish it with the smaller number of moles and continue on to the mass of product. That works, but I found that it requires a little more thinking than my method. So my method, we're just going to do two calculations that are the same. So I'm going to get rid of this. I don't know why that's so fun, but it is. So here we're going to go to mass of product. And here we're going to go to mass of product. And then we're going to ask ourselves which is smaller. And then we're not going to have this step down here. So we're going to do two calculations, grams to moles to moles to grams. We're going to go all the way to the mass of product. We're just going to pick the smaller one, and that's our theoretical yield. It's one extra step, but we'll see when we do some examples that this conversion factor is the same for both of the equations. So it's really very little extra work, and you don't have to think about it as much. You can just do two of those same gram to mole to mole to gram calculations. Pick the smaller answer, you're done. Okay? Let's do an example. Ammonia can be synthesized by this reaction. What is the theoretical yield of ammonia in kilograms that we can synthesize from 5.22 kilograms of hydrogen and 31.5 kilograms of nitrogen? So I'm going to use the balanced chemical equation to organize this information. They tell me I have 5.22 kilograms of hydrogen. So I'm going to write that in there. And 31.5 kilograms of nitrogen. What is the theoretical yield of ammonia in kilograms? So question mark, kilograms. So we know this is a limiting reactant problem because it says so up there. But what if you're just given this problem on an exam without any title on it? How do you know that it's a limiting reactant problem, that you need to do two calculations? Well, you're given two masses. You have two reactants, and they give you the mass of each of them. In the previous section, when we did problems like this, they just gave us the mass of one, and we either assumed or they told us there's plenty of the rest. So when you have two amounts, you have to do two calculations. So we're going to go grams to moles to moles to grams. These are kilograms, but we can deal with that. For each of these, so let's do the first one first. So 5.22 kilograms. I'm going to write that kilo in red. We're just going to ignore that. It's going to sit there uncanceled, and then at the end it'll still be there, and so this is the way I like to do these. So that's kilograms of hydrogen. I want to convert that grams to moles. I want to do moles of hydrogen to moles. Next is moles of the product. And then I want to go to grams of product. Grams to moles to moles to grams. I'm writing grams of H2 down here. I'm canceling out grams of H2. I'm leaving the kilo there. There's other ways to deal with the kilo. This is what I'm doing. Where do we get the numbers for this mole ratio? I know it's Monday morning, 8:20 in the morning, but wake up, please.
From the equation.
From the equation, thank you. So here we see 3 in front of H2. So I'm going to put a 3 in front of moles of H2. There's a 2 in front of NH3. This equation is saying I will get 2 moles of NH3 if 3 moles of hydrogen react. Okay? The first and last terms are molar masses. Okay? We should be getting accustomed to doing those. H2, that one's pretty easy. It's just 2 times the mass of hydrogen. So that's 2.016 grams per mole of hydrogen. And then for ammonia, it's nitrogen plus 3 hydrogens, which I sadly happen to remember is 17.034 grams. And that's 1 mole of ammonia. So I'm going to do the math. 5.22 divided by 2.016 times 2 divided by 3 times 17.034 equals. I'm always going to be thinking about significant figures. The starting number has 3 significant figures. My molar masses have 4 or more, and my mole ratio is exact. So this should have 3 sig figs. I don't want to round it yet. So I'm just going to write my 3 sig figs and then 2 extra digits. And the unit there, I've got grams of ammonia and the kilo still. So I have kilograms of ammonia. Any questions about that? Now I'm going to do the same type of calculation using the other reactant. So that other reactant, I've got 31.5 kilograms of nitrogen, N2. Grams to moles to moles to grams. So I convert to moles of nitrogen, and then I convert to moles of ammonia, and then to grams of ammonia. So I put the previous unit in the denominator so they cancel out. And then here, again, I'm canceling the gram, but not the kilo part. Just letting it sit there. Mole ratio. What number goes on top? 2. What number goes on the bottom? 1. Those come from the coefficients in the balanced chemical equation. 2 moles of ammonia from 1 mole of nitrogen. This molar mass for nitrogen is 2 times 14.01. That's 28.02. I did that in my head. Don't do that on an exam because your brain will mess up. It just happens. Or do it in your head, but check it on the calculator. And now look at this one. This is exactly the same factor as the first one. So there's very little thinking here. Just copy it down. We already figured it out. So then we do the math on this one, 31.5 divided by 28.02 times 2 times 17.034. And again, we should have 3 significant figures, 38.299. Anybody else get that? Thanks. And that would be kilograms of ammonia. I have 2 answers. I can only have 1 answer to what's the theoretical yield. The smaller one. Like with the pizzas, we had 5, 4, and 3. We can't just add them together, right? That would be silly. Sometimes students do that with these because it's harder to understand, it's harder to visualize what's going on here than it is with pizzas, right? We pick the smaller one. So this one's smaller. So let's round that to the correct number of significant figures, 29.4 kilograms of ammonia, and that is the answer. On a multiple choice test, you have to pick an answer. If it's an open-ended show your work problem and you don't indicate which of these is your answer, it will not be completely correct because you have to pick an answer, okay? So this is the theoretical yield. It's the smaller amount. What's the limiting reactant? The limiting reactant is the reactant that gave us the smaller amount. I'll sometimes have students tell me that the limiting reactant is 29.4 kilograms of ammonia. Well, that's not the reactant, right? Here's the theoretical yield. You go back and you find out which of those gave you the smaller. So hydrogen is the limiting reactant, and I sometimes abbreviate that LR. This question didn't ask for that, but sometimes it does. Any questions? Let's do another one. Mining companies use this reaction to obtain iron from iron ore. Iron ore is the stuff they dig up out of the ground. It's a mixture of dirt and useless things and compounds that contain iron. And so this particular iron ore is iron 3 oxide. So they use this reaction, iron 3 oxide, they react it with carbon monoxide, and they can get iron and carbon dioxide as the product. So the reaction of 167 grams of Fe2O3 with 85.8 grams of CO produces 72.3 grams of iron. Determine the limiting reactant, theoretical yield, and percent yield. So I'm going to use the equation to organize the information. They tell me I have 167 grams of that, Fe2O3, 85.8 grams of CO, and it produces 72.3 grams of iron. So they're asking for three things: limiting reactant, theoretical yield, and percent yield. What's different about this problem? How many numbers did they give us? They give us 3 numbers. Is this the theoretical yield? No. What is that? Why did they give us this? When they reacted this much iron oxide and this much carbon monoxide, it made this much iron. That's the actual yield. That's how much they actually got. So this is the actual yield. As I mentioned before, in a problem, they have to give that to you somehow. Sometimes they'll come out and say, the actual yield was this, and that's easy, but this one they didn't actually say that. How do we figure out the limiting reactant? Well, we kind of have to do the theoretical yield first, right? We'll take this amount of Fe2O3 and figure out how much iron we could make. And we'll take this amount of CO and figure out how much iron we could make. And the one that gives us the smaller number is the limiting reactant. And the smaller number is the theoretical yield. So let's do that. So 167 grams Fe2O3. So grams to moles to grams. So grams of Fe2O3 to moles of Fe2O3 to moles of the product. This is the product that we're interested in. CO2 is also a product, but they gave us an actual yield of iron, and we're wanting to find iron, so everything needs to go to the same reactant. If you calculate the mass of CO2 and compare it to the mass of iron, that doesn't mean anything. So we're going to moles of iron. Sometimes in the homework, they'll give you a problem, and there's two products, and they're going to ask you what the limiting reactant is, and they don't tell you which product you're interested in. If they're just asking you about the limiting reactant, You can pick one or the other. Just pick one and do both calculations for the same one. The moles of iron go down here. And this will be moles of Fe2O3. And this will be grams of Fe2O3. You don't have to mess around with the kilo business on this one. Mole ratio in the middle from the balanced chemical equation. I need moles of iron. I find iron in here, and I take the number in front of it. So 2. On the bottom, I've got Fe2O3. I find that in the chemical equation. The number in front of it is an understood 1, so I can write 1 here. This last one is easy. Because iron is an element, I believe that's 55.85 grams per mole. So I just find that one on the periodic table. This one I do have to calculate, so I'm going to do that up here. Fe2O3. So I've got 2 times the mass of iron plus 3 times the mass of oxygen. $159.7. That's grams of Fe2O3 per mole. Yes?
Are they always rounded to 4 significant?
That's a good question. Are the atomic masses always rounded to 4 significant figures? No. 4 is the minimum number I think you should use. Because many of the problems have 3 significant figures. You don't want any of your conversion factors to be limiting the number of significant figures in your final answer. I use 4 because the periodic table I started teaching off of had 4, and I've got a lot of them memorized. And so it just makes things faster and easier. It is better if you use more, but it's not necessary. Okay? Good question. So I got 159.7 grams per mole for that one. So we do the math. And thinking ahead, we think, well, this has got 3 significant figures because of the 167. I'm just going to write down 2 extra digits and call that grams of iron. That may or may not be the theoretical yield. We have to do the other calculation with the other reactant to find out. So the other reactant is carbon monoxide, 85.8 grams of CO. So we go to moles of CO. And don't let that oxygen shrink, because then you start to think it's cobalt. We're going to go to moles of iron and grams of iron. Grams to moles to moles to grams, dimensional analysis, units go in. That tells us where to put the numbers. I like to start with the mole ratio because I think it's the easiest. Here's iron, it's got a 2 in front of it, so put a 2 there. Here's carbon monoxide, which is the thing I have on the bottom. It's got a 3 in front of it, so I write a 3 in front of it there. Bang. This one's easy because it's exactly the same as the calculation above. 55.85 grams per 1 mole. And then the first one, I need the molar mass of carbon monoxide, which is 12.01 plus 16, 28.01. So now I do this calculation. 85.8 divided by 28.01 times 2 divided by 3 times 55.85 equals. And this one comes out 114.05 grams of iron. So which reactant is the limiting reactant? The carbon monoxide. This is the smaller amount, so carbon monoxide is the limiting reactant. So carbon monoxide is limiting reactant. That's the first question, the limiting reactant. The theoretical yield. This is the theoretical yield. If I'm going to report it as a final answer, I'm going to round it to the correct number of significant figures. So Ty, theoretical yield, is 114 grams of iron. So that's one of my answers, and I've got this answer over here. And then it asks for the percent yield. So percent yield is the same idea as all percentages. It's the part over the whole. So percent yield is our actual yield over the theoretical yield. So actual over theoretical times 100%. So my actual yield was given 72.3 grams. The theoretical yield, we calculated 114.05 grams. I want to, I've got those extra 2 digits, I want to keep them, just to avoid any rounding errors. And then this is times 100%. What happens to the units, gram? They cancel out. So when you're calculating a percentage, the unit always ends up being percent. It's not grams percent or grams or anything like it. It's just percent. So 72.3 divided by 114.05 times 100 equals. And this result should have 3 sig figs. 63.393%. And then rounding, we'll say 63.4% yield. Any questions? Do you think the owner of the mining company would be happy with you if you increased the percent yield? Yeah. The percent yield gives you an idea of how efficient your process is. The closer to 100, the better. Can you ever get a percent yield that's over 100%? You can, but it's because something is not right. Because can you make more iron than is theoretically possible? No. But you can have things happen like you get a contaminant in your product. Maybe your product isn't quite dry. It's something you precipitated and it's not quite dry. So when you weigh it, you're getting the mass of water plus the mass of your product. That can make your percent yield seem over 100%. You could have a co-precipitate. There's a lot of different things that can happen. If you get a percent yield over 100%, that means that there's something wrong going on. Not necessarily that you calculated wrong, but something's not quite right. Any questions?